So following last class where we found standard deviation, this time we're going to interpret it. So a reminder that standard deviation is the measure of the typical amount that an entry deviates from the mean. So it's basically the average distance away from the average. Okay. The more spread out that they are, the bigger the standard deviation is. Okay. So if we look at our graphs, this first graph, all of our data entries are the same. So everything is at 5. So it is not spread out at all. So it has a small standard deviation. Now this third graph, they're super spread out. They range from 2 to 8 with heavier on each end. So since it's very spread out, it's going to have a larger standard deviation. Now graphs like the middle one are what we're going to look at today. So the mean is right in the middle. And they kind of have this normal curve. You've probably seen it in science. It is called the normal curve. The normal curve is nice because it's symmetric. So if we cut it right in half, fold it over, it's like a butterfly, so it's symmetric on both sides, with the mean being in the middle. And it gradually gets lower as you go further out. So if our data falls in that normal curve, we can use the empirical rule. So it has to be symmetric. And bell-shaped. So it's going to look something like this. And if we have a symmetric bell-shaped distribution, we can follow these characteristics. That 68% of our data fall within one standard deviation. So that's adding 1 and subtracting 1 from the mean. So from the mean, we would add 1 standard deviation and we would subtract 1 standard deviation. If we go out 2 standard deviations, we have 95% of our data that falls within there. And if we go within 3, we have almost all of our data, which is 99.7%. Now that's not accounting for any outliers. Those are kind of the 0.3% that fall within there. Okay, so it's called the empirical rule, but it's also sometimes called the 68, 95, 99.7 rule, because those are the 3 increments within 1, 2, or 3 standard deviations. You will need to know these numbers. So we'll have pictures like this, and we're going to kind of fill one out on the next example, so we'll get a lot of practice with it. But from our mean right in the middle, we subtract 1 standard deviation and we add 1 standard deviation, and that 68% is split on each side. Then to go out 2, so we subtract 2 standard deviations and then we add 2 standard deviations. That includes the 68 from the previous one, but then we add on kind of 13.5 onto both ends. That each one of those percentages are split evenly down the middle since our graph is symmetric. Okay. So in this survey, we're given a sample mean of 64.3 inches. We're also given the standard deviation. So on these problems where you're asked to interpret, you might be asked to find the standard deviation, but most of the time they're going to give you the mean and the standard deviation. So we want to know the percent of women whose height are between these two intervals. So we need to find how far out from the mean those intervals are. So if we start in the middle with 64.3 inches, I'm going to add 1 standard deviation. So adding 2.62 inches, and that becomes 66.92. We're going to subtract 2.62 inches. We get 61.68 inches. Okay, we need to go out even further, so go 2 standard deviations out. So this one right here, we have our mean plus 2 times our standard deviation, 2.62, which is 69.54. We're going to do the same thing, except we're going to subtract it. So 64.3, our mean, minus 2 times 2.62. And although we know our interest, or like the interval that we're interested in, let's go ahead and label that last one so we get a good idea. On this third one, we know we're 1 more standard deviation, so we could take this 69.54 and add on 1 more. Or you could do what we have been doing with the mean and adding 3 times the standard deviation. Doesn't matter which way you get there. And then do the same for subtracting. So we want to know what percent of women fall within 59.6 inches to 64.3. So it's kind of in this region right here. I think going back to a normal curve that's labeled like this one is kind of helpful because each section is labeled. So if we have 68 on this whole region, that means we have 34 in this section. And then if we have 95 in that, or let's do this. Let's backtrack a little bit. If we have 95 in this whole entire kind of, let's arrowed in blue, this is only half of it, so we need to do 95% divided by 2 to get the percentage of it. So it's 47.5%. Okay. Chebyshev's theorem is the last thing we're going to kind of cover in this video for the day that I'm gone. It's not something that we're going to test over necessarily, but we do want you to kind of see it. So this happens when the data is not symmetric, but it is bell-shaped. So maybe it looks like this and it goes on. So it's skewed to one side. So we have the percent of data within some number, k is just our variable, of standard deviations can be found with this formula. Okay. It is not very accurate in this formula, and that's why we're not going to test over it, but it is good to know. So if k was equal to 3, so if we wanted to know within 3 standard deviations of a non-symmetric curve. We would plug in 3 for k, so 1 minus 1 over 3 squared is 1 over 9. We got around 8/9 of the data, which is almost all of the data, which mirrors our empirical rule. Okay. So that's about 88.9% within. You need to show these notes to the sub, and she will get you the next assignment.